What actually comes out of a subsea oil well is absolutely nothing like the refined crude you might picture putting in a gas tank. Welcome to this explainer. Today, we are setting out on a deep dive into the absolute heart of an FPSO. That's a floating production, storage, and offloading vessel. We're going to look right at the massive topside process plant sitting up on the deck. Because, let's be real, this isn't just about storing oil. It's about the intense, high-stakes core engineering required to tame the totally chaotic fluids bubbling up from beneath the ocean floor.
So, do pure oil and gas just naturally flow straight out of a subsea well? I mean, it's easy to imagine this pure black crude cleanly pumping from the earth. But actually, scratch that. What really erupts from a subsea wellhead is this violent, superheated, high-pressure, multi-phase mixture. We're talking oil, gas, water, sand, scale, and some highly corrosive corrosion products all mixed together in one dangerous mess.
Okay, let's dive into this. To untangle all this chaos, we're going to follow a single drop of fluid through 5 main stages: separating the multi-phase mixture, treating the produced water, processing and compressing the gas, injecting crucial chemicals, and finally, looking at enhanced oil recovery techniques. First up on our journey, Section 1, separating the multi-phase mixture. This is where we begin the heavy lifting of detangling and stabilizing that raw fluid. The moment this multi-phased fluid arrives on the deck of the FPSO from the subsea wells, it's immediately routed right into the production separator train. Think of the topside process plant as this massive, incredibly intricate web. Its entire job is to systematically untangle the oil, gas, and water into safe, manageable, export-quality streams. The core of this detangling actually happens across a progressive 3-stage separation train. We start at the high-pressure separator, which operates at a whopping 60 to 80 bar. Then, the partially degassed fluid moves to medium pressure, and finally, the low-pressure stage. Think of it exactly like slowly unscrewing the cap on a shaken bottle of warm soda. As the pressure drops at each successive stage, the lighter hydrocarbon gas components naturally flash out of the liquid crude as vapor. By progressively stepping the pressure down like this, the vapor pressure of the oil itself is reduced until it's fully stabilized and perfectly safe for cargo tank storage.
Inside one of these massive separator vessels, it's really just simple fluid dynamics taking over. The gas flashes upward and passes through a mist extractor to catch any stray liquid drops. Meanwhile, gravity is doing all the hard work down below. Because oil and water have different specific gravities, the oil naturally forms a middle layer right on top of the water. Physical baffles and a really clever weir system, which basically acts like a tiny dam, allow the lighter oil to spill over into a separate chamber. It's brilliantly simple, completely isolating the 3 phases.
But wait, even after those 3 big pressure drops, the oil isn't perfectly pure just yet. It still holds this really stubborn emulsion of microscopic water droplets. To fix this, the separated oil is passed through an electrostatic coalescer, and this thing is wild. It literally blasts the oil-water emulsion with 10,000 to 30,000 volts of electricity. This intense electric field polarizes the suspended water droplets, forcing them to collide, merge into larger drops, and then just sink to the bottom by gravity. It is highly effective, bringing the final export oil down to a strict BS&W, that's basic sediment and water, specification of less than 0.1 to 0.5%. All right, moving right along to Section 2, treating the produced water. Now we have to deal with the water we just stripped out of the crude. This produced water is highly toxic. It's full of dissolved gas, dispersed oil droplets, production chemicals, and sometimes even naturally occurring radioactive material. So we absolutely cannot just discharge it directly into the ocean. It has to run through a dedicated step-by-step treatment train. First up, it goes into a degassing tank at near atmospheric pressure just to release any dissolved gases. Then the water moves into hydrocyclones for fine separation. And finally, it enters a flotation unit to skim off the very last traces of oil. Now, what's really fascinating about a hydrocyclone separator is that it actually has absolutely no moving parts. None. The water is forced tangentially into a tapered tube, and this creates a violent, spinning vortex. Centrifugal force physically throws the denser water out to the outer walls and down to a bottom outlet, while the lighter oil droplets get forced into the center core and pushed out the top. This clever mechanical spin separates oil droplets down to an incredibly microscopic 15 microns. And that level of precision brings us to a critical regulatory number, 15. After the water passes through that final flotation stage, an online meter continuously measures it. The absolute strict limit is an oil concentration below 15 parts per million before discharge.
If it spikes even a little bit above this limit, the system automatically recycles the water right back through the treatment train. This is exactly how the facility actively protects the fragile marine environment from any contamination.
Which brings us to Section 3, gas processing and compression. This is the lightest phase of our fluid, but handling it requires some incredibly intense engineering.
Dealing with gas at these pressures introduces some incredibly high stakes. Gas from each separator stage is first scrubbed to remove entrained liquid. Why? Because if even a tiny, microscopic amount of liquid makes it into a centrifugal compressor impeller spinning at high speed, it causes catastrophic erosion. But an even bigger threat is compressor surge. This is a terrifying phenomenon where flow suddenly reverses back through the compressor. The violent vibrations will physically destroy a multi-million-dollar machine in a matter of seconds. It's a constant balancing act. But once safely compressed, this gas is incredibly valuable. It's used as fuel gas to power the turbine generators on the FPSO, completely replacing diesel, or it's re-injected into the reservoir to maintain pressure, exported via pipeline, or, as a very last resort, flared off.
But before any of that high-pressure compression can happen, the gas must be perfectly primed, meaning it has to be dehydrated and sweetened. Wet gas is forced up through a contactor tower against a downward cascading flow of triethylene glycol, or TEG. Think of TEG like liquid blotting paper. It absorbs the water vapor by hygroscopic action. This water-laden TEG is then heated in a reboiler regenerator to boil off the water and recirculated right back into the tower in a continuous loop. On top of that, if the gas is sour, meaning it contains dangerous hydrogen sulfide or carbon dioxide, a process like Selexol is used to dissolve and strip away those hazardous acid gases.
All right, let's look at Section 4, crucial chemical injection systems. Now we're shifting our focus to the unseen chemical battles being waged constantly within the thousands of feet of pipework.
You see, down in the freezing depths of the ocean, gas and water can combine to form these nasty ice-like plugs called hydrates, which can catastrophically block a flow line or riser. To fight this, engineers inject chemicals directly into the subsea piping. Methanol is highly effective and used in large volumes for emergency treatments to melt blockages. However, for continuous, day-to-day hydrate prevention, monoethylene glycol, or MEG, is the preferred choice. Why? Well, because MEG can actually be recovered on the FPSO, heated, regenerated, and pumped right back down, making it way more economical. And hydrates aren't the only enemy down there. Every massive operational threat has a specific chemical counterattack. For example, if sulfate-reducing bacteria are left unchecked, they produce highly toxic H2S gas as a metabolic byproduct, completely turning the reservoir sour. To prevent that, we continuously inject biocides. When seawater mixes with reservoir water, hard minerals can crystallize and literally choke the pipes, so we pump in scale inhibitors. And to stop the crude oil from cooling and solidifying into a thick wax, pour-point depressants are dosed right into the flow. It's an absolutely relentless, precise chemical war going on 24/7.
Finally, that brings us to Section 5, Enhanced Oil Recovery Techniques, or EOR.
As a reservoir matures, its natural pressure steadily declines. The FSO can't just sit there and wait for the oil to stop flowing. It has to actively fight back. When natural pressure isn't enough to push the fluid up thousands of feet to the surface, we deploy some powerful mechanical and thermodynamic solutions. We use gas lift, which is actually the simplest and most widely deployed EOR method on FPSOs, where we inject high-pressure gas down the well annulus through downhole valves to aerate and lighten the fluid column. We use electric submersible pumps, basically lowering physical motors down into the corrosive reservoir fluid to push the liquid up. And of course, we use water injection to maintain the reservoir pressure itself.
Water injection is an incredibly reliable EOR method. By taking treated seawater, or even recycled produced water, and injecting it into the outer flanks of the reservoir at an immense 400 bar of pressure, it creates an artificial drive. It's literally a massive wall of pressurized water that sweeps the remaining, stubborn pockets of oil directly toward the producing wellbore.
But here's the catch. You can't just pump raw seawater into a multi-million-dollar well. Seawater is packed with dissolved oxygen, which would instantly rust and corrode the downhole steel tubing. Enter the Minox system. This extreme filtration process uses nitrogen stripping and a methanol-palladium catalyst to chemically scavenge and remove oxygen from the injection water, and it brings it down to an astonishing 10 parts per billion. That's billion with a B. It stops oxygen-induced well corrosion dead in its tracks.
So, to quickly recap Module 6, we've seen how three-stage separation progressively degasses and stabilizes crude, how electrostatic coalescers remove emulsified water, and how water treatment hits that strict 15 ppm standard. We covered the chemical warfare keeping pipes clear, the TEG and Selexol gas processing, and the massive EOR methods pushing field life way beyond natural flow. But it leaves you wondering, as subsea pressures inevitably continue to drop, just how far into the future can the engineering on these floating titans extend the life of a dying well before physics finally wins? It's a fascinating, ongoing battle of innovation. All right, Module 6 was a big one. In our Module 7 explainer, we are going to untangle the massive piping and pumping systems that connect all of this amazing machinery together. Subscribe, keep learning, and I'll see you there.